Hi everyone, we're going to get started. Welcome to the last NetSeminar of this academic year. We'll continue in September. Today we have Guido Appenzeller from VMware. Guido is a very accomplished person in the software-defined networking world. He started out with founding Voltage Security and then co-founded Big Switch Networks. Spent a few years as a consulting assistant professor at Stanford University, and then finally now he's the CTSO of networking and security at VMware. So without further ado, here's Guido.
Perfect, thank you. All right, so today I want to talk about software-defined networking. Should be fun. There's a couple of people here who I think can take credit for co-inventing it in the audience. I'll try to keep this controversial here and spark a discussion. So if you have any questions or disagree, please interrupt me at any time. Does everybody know where the term software-defined networking comes from? The origins.
Paper?
Yeah, good guess. Yeah, correct. So there was this OpenFlow project here at Stanford, which many of you know, which we're sitting over in Gates on the third floor. And Kate Green from the IT Technology Review wrote an article about us and was sort of asking, how's this category called? And I think our answer was along the lines of what category, right? We have this one research project, and she was seeing something bigger. And so she was writing about software-defined radio, and so she was looking for some, well, it's like software-defined radio just for networks. So she called it software-defined networking, and here we are. Who can define what software-defined networking is? Nobody? That's good, because I'm not sure I can do that either. We'll get to some examples later, but there's a lot of confusion around that, and depending who you ask, you get actually very, very different answers. But let me actually start out by talking about why SDN. So when we started OpenFlow, and I think when the whole SDN movement started, there were sort of, I think, it was one primary reason to do this. And this is actually a slide back from 2009. Back in 2009, and to some degree still today, the perspective on the networking industry was that networking as an industry had fossilized, right? That essentially there was no more innovation going on. You had this. The theory of how you build computer networks is you have this nicely stacked architecture of a specialized packet forwarding hardware, so basically a networking chip made by somebody. You have an operating system on top. You have, let's call them the apps, the things that implement the actual protocols. And if you looked at how this looks in reality, this was all one vertically integrated stack, so there were no clean APIs. You couldn't replace any of these pieces. As a result, all of this came as a monolithic box, and there was no innovation. Right? And the hope was with SDN, we can actually change this. The second problem was that, and still is, that in networking, most of the functionality is driven by standards, right? If traditionally you want to do something in your networking, you need a new protocol. To get a new protocol, you need to get it through the IETF. So you have an idea, you throw that into a standards process. It takes 10 years. In some cases, maybe shorter, but now 10 years is actually pretty reasonable. And at the end of the day, you have something else coming out which may look actually a lot more complicated than the thing that you threw in. Right? If you look at something like the IPsec standard, right? It starts with a simple idea of let's encrypt packets, and ends up being, I think, 10 RFCs in the original invocation, about this much paper, right? A complete mess that nobody can implement, and it has gotten a lot of complexity. So that was the frustration that built up around that time. So the goal was to turn networking to more of a software industry, right? Because for a very long period of time, networking had not been a software industry, but a systems industry, right? I think the way how we bought network equipment over the past 15 years, as Charlie can attest, the way he bought network equipment over the last 15 years is you buy a box, from a vendor. The vendor will build the chip. Maybe there's merchant silicon there today, but mostly the vendor will build the chip. The vendor will build the system. The vendor will put the software into the system. Your only interface to it is a narrowly defined CLI, right? And whatever the vendor thought, is a good idea to do with this box, this is what you can do, right? Very narrowly defined. And everything comes as one package. Now, compare that to how the PC industry works. So if I buy a PC, usually, I go to Dell. Maybe I can pick what CPU do I want to select, Intel or AMD. Then I have a lot of different vendors that actually make the box, like HP, Dell. I can go white box with Supermicro or Quanta. Lots of different manufacturers. And then I can pick an operating system on top, maybe a virtualization layer, and then I have powerful tools to automate the whole stack. So it would be crazy to think that from Dell I can only buy PCs with Zen and Windows and AMD under it, right? Obviously, you can mix and match. That's great. Well, with networking equipment, that's still the case, right? I can't buy a Cisco with the Arista operating system on top, or vice versa. So it's vertically integrated, locked in. Now, why does this matter, right? The problem with these vertically integrated, locked-in type architectures is that they tend to slow down innovation. And let me sort of make this very concrete, right? In 1996, I was installing servers. I'm probably dating myself here. No, but back then, you were taking a CD. Does anybody remember what a CD is? So you're taking a CD, that's the silver disk, right? You put it in the disk drive, you have a serial cable with a terminal, right? And you would start installing Linux. If you're lucky, 2 hours later, you'd have a Linux installation on the server that you could give somebody from the application team to actually do work. That's how you install this. If you're working in enterprise, typically today, and you need a new server, what do you do? It depends a little bit on the enterprise, but in many cases, you go to the server self-service console, you pick your base image, and you say instantiate. Right? Anybody ever used Amazon? Right? And like, yeah, take this, Linux-based image, instantiate, and 30 seconds later, you have a server up and running. Right? So we've made huge advances in terms of how we manage servers over these, almost 20 years. So this is how you administered the network switch in 1996, and this is how you did it in 2015. Right? Basically, nothing has changed, right? You would use, this is actually an actual example here from 1996 out of an auto manual. Now, I think the only thing you probably wouldn't have anymore is the serial interface there. But everything else in terms of the same commands still work, the way how you manage your network works, very little change. There's actually one tiny change, which we went from Telnet to SSH. But that is pretty much structurally in terms of the difference between administering servers 20 years ago, network switches 20 years ago and now. Here's a more graphical version from one of another presentations. To compare compute evolution over this time, we've made huge advances. Right? The network evolution, though, in terms of tools, we are sort of still stuck in the stone age. And this is actually pretty typical, right? Hardware-based industries tend to innovate much, much slower than software-based industries. Right? You have much higher capex. Imagine you want to do a classic networking startup, right? There were a couple of good examples like Procket or these guys, where basically, well, you have to hire some chip designers, you have to hire some software designers, you have to hire some system designers. Capital requirements probably $100 million. In today's market, more like 150 million. And then you basically, 5 years later or 4 years later, you have a product and then you just start selling, right? That's a terrible climate for innovation, right? Compared to the pure software industry, if you want to start a new software company for a PC, basically your starting cost is a couple of $1,000, right? You need development toolkits, you need a server, and you're good to go, right? So I think this was the frustration. I'd say, in networking, nothing is happening. I remember when Nick suggested I should come back to Stanford as a consulting professor, he said, hey, Guido, maybe you can start a company. And I told him, Nick, that's the stupidest idea I've ever heard. I mean, who in his right mind wants to start a networking company? This is so fossilized, this is just no fun. So that was 2008, OpenFlow 2009. Right, 2010, I left Stanford, started Big Switch, parallel to my team, had started Nicira Networks. And in those 7 years since the term, six years since the term SDN was created, 7 years since we started OpenFlow, the whole industry has taken off. Right? SDN today is unbelievably successful. Right? It's an extremely rare case where you see an idea from academia go to broad-scale industry adoption in this short period of time. Right? It's very, very exciting. In the meantime, I hope we've learned a little bit of how SDN works and how it doesn't work. And so my main goal here today is to share some of the learnings. And I typically stay at the architectural level and not dive deeper into algorithms or data models. I also try to give you an idea of how this is actually used in industry. Because in my experience, if you're sitting in academia, it's sometimes really hard to understand what's actually happening in the large-scale data centers, where people are spending billions of dollars. And how does that link up to what you're doing every day? All right. So this is one of the original slides actually I was presenting in 2009. Right? The very basic idea we had back then of software-defined networking was the following. Right? You would take a switch down here. You have the data path, right? This is a specialized networking silicon. You have the control path, the software. In software, you add little stuff to the protocol, the OpenFlow protocol. And then you take an SSL connection between the controller and the OpenFlow protocol. If this thing is standardized, right, then you can now basically go out, buy a controller from one company, buy a switch from another company, and they work together. Right? Great idea. Here's another, this is a little bit later from Big Switch, right? Same idea. So we have the controller platform, ideally with APIs, we have self-code APIs, probably OpenFlow, then we have all kinds of switches from all kinds of vendors and hypervisor switches, and they all work together. Beautiful. For a company adopting networking, this is actually a big deal. Let me explain why. I mean, typically today, once you start buying hardware from one vendor, you're sort of locked in, right? Because you start training your people, those CLIs, you have all your spare parts, you have all your support contracts. If you ever want to switch, say, from Cisco to HP, it's a fairly painful thing, right? I mean, campus, you can do it more easily. In the data center, doing this wholesale is almost impossible. So this idea of being able to go from vendor A for the switch to vendor B for the controller, incredibly appealing, right? When I talk to large customers in 2010, 2011, they all love this idea, right? This is huge for them, right? So who can tell me an example, an actual deployment that works in this model? Controller from company A, switch from company B, working together in production in the company.
There might be a few data centers in China that do that, maybe.
Controller from company A. There's also two external vendors. So they have bare metal deployments, I know, and I don't think of third-party centralized control planes. So actually, I've never seen one. The original architectural model we were promoting for OpenFlow back then, I've never seen a single deployment of this type in production in my life in the world. Right? It sounded great on paper, but in practice, at least I haven't seen it materialize yet. So in China, I know two of the hyperscale guys. They basically have switches from one company, but they have developed their internal controllers. So that doesn't quite count. As far as there's something in the WAN space, I have less visibility there, but at least in the data center, I'm pretty certain this, today, the classic OpenFlow model does not exist. Right? So why is this? Right? It's not that SDN didn't work. SDN is everywhere. It's actually not the protocol either, because many of the SDN solutions that are deployed today, under the hood, if you actually look at the bits going on the channel, they use the OpenFlow protocol. Distributed, big switches, lots of other companies. I think fundamentally, my guess is there were two reasons. And the first one was, imagine you're a hardware vendor, right? What's your incentive in basically commoditizing yourself and letting another company build a controller that takes some of the functionality out of your switch? Right? They didn't want to do that. Right? And we pushed it pretty hard. We tried all kinds of things, but it was really difficult to move that ball forward and get them to learn this. So I think there's a second point, which is if you have systems, that are basically all deployed by one organization, right? There's very few cases where you started out with a standards-driven process. Right? Typically, there was a de facto standard created and then later adopted. It's a little bit different if you have like web server and web clients, where you always need interoperability. But if basically the thing gets deployed as one stack, it's really hard to do. So let me try to do this a bit more quantitatively. So imagine for OpenFlow, there's a new chip coming out with a new feature, right? And so this is, for example, VXLAN for the Prime Plus. So usually when the new chip comes out, as a vendor, you can get access to the specs and what it does long before this becomes public, right? And some features stay under NDA pretty much forever. In any case, you have about a year, when a new chip is being shipped, before this thing's public. If you want to get this into an OpenFlow type standards development model, you probably have another year or so to get the standard shaken out, right? I mean, this thing doesn't perfectly align necessarily, and so after 1 year, you have a standard. Then the vendors start implementing that on switches. If you're an independent software developer, then you start your controller development, right? That takes a really, really long time. Specifically, 4.5 years, probably the high side. You can try to shave off a little bit by compressing this. Maybe you can start talking about the OpenFlow standard before the feature is out of NDA, because there's a corresponding RFC. But it takes a really long time, right? And more importantly, if you look at chip generations, you probably want to have at least one chip generation in that, the next chip generation in that time. Now, if you compare it with an integrated model, right? If you're a software manufacturer, you have a relationship with Broadcom. Basically, as soon as they tell you this new chip is coming, right, you can start implementing this thing. You can start thinking this through. As soon as you can get a sample, which is usually way before this thing is actually public, right? As soon as you get a sample, and a board that is on it, you can start developing the software. You can start developing the controller at the same time, and you can ship the solution much quicker than you can do it with a standardized process. So I think in addition to switch vendors just not wanting to do it, I think this is the second problem, that in a very rapidly evolving market, where basically, your technology is turning over very quickly, it's really hard to follow a standards-based model. So instead of this original open flow model, I think so two other models evolved that today, if I look at industry, are the predominant ways of deploying software-defined networking. And the first one is obviously hypervisor overlays. So here the basic idea is to say, we just give up on those networking guys, let's move everything up into the software. And this is what the Zero pioneered. We have hypervisors. Now I'll show you in more detail how this works in a second. And the second one was bare metal switching. We're basically saying, okay, we need to own both sides of the equation. Let's do it. Let's put software on the switch. Now, there's lots of other things right now that are marketed as SDN. Right? For example, Cisco with the ACI product, they have a much larger marketing budget than I have, so that's being widely named as SDN. There's things like Zygo had an I/O virtualization technology, and they labeled that as SDN. So basically, anything new in networking at the moment gets the SDN sticker. Right? I don't think there's any single definition of what SDN is or isn't. Right? I mean, for me personally, the way I would personally define is actually to say, does this get us back to the original idea of being able to innovate hardware and software at different speeds? Right? I mean, where we came from when we started this was to say, look, we're frustrated by how slowly the hardware is evolving. Right? Can I pick best of breed hardware and pick software separately? Right? And we can do that with overlays, because you basically just say, okay, hardware is whatever it is, it just needs to do IP forwarding and move all functionality into software. You can do it with bare metal switches, because it can replace the software. If you have a completely, there's other definitions of SDN, for example, a centralized control plane, right, where you say, as long as you have a central controller that controls lots of switches, that's SDN. Right? I mean, under that definition, I think pretty much any fabric out there would be SDN, right? And it wouldn't matter if this is open or closed. Some technologies that we predate SDN would count as SDN. So look at ATM might be SDN by that definition. So in this talk, I'm going to focus on these two. So let's look at the architecture, right? So this was the open flow model. We said, okay, we're going to have a controller from one party, we're going to switch from another party, and we're going to add these SDN points. The problem is, basically, for rapid innovation, these things being developed by different organizations, this standard between by a third organization was very difficult to make work sometimes. So for network overlays, for bare metal switching, the idea to write this up is to say, okay, let's just completely replace the software on the switch, right? So instead of having the software on the switch being made by the same company, let's have the software on the switch made by a different company. And so today you can go to Dell or HP or various Taiwanese vendors, basically buy a cheap switch without any software, put your own software on top of it, then you put a control plane on top, and you have an SDN. The other model was to say, let's just give up on networking overall, right? L3 porting, we're never going to change these guys. So let's just require very, very simple networking. Instead, we introduce additional level of switches in the hypervisor, and then we can basically do everything on top. And we don't need to change the network. So architecturally, network virtualization is a very simple idea. Right? Everybody here knows server virtualization, I assume. So have you used like VMware or Zen or KVM or something like that? So the basic idea of server virtualization is to say, have a physical server, put a hypervisor on top, and this hypervisor creates these virtual machine abstractions. Basically, every virtual machine, everything running in a virtual machine, thinks it's running on its own server. That's sort of created an abstraction layer on top of the hardware. The idea for networking is fundamentally the same. For virtual network, it's fundamentally the same. We're saying we're taking a physical network, and put a hypervisor on top. This is a network hypervisor. And each and every application is running on top is going to think it's running in its own network. And we can now create these networks in software. And the way how you do it is that basically in the hypervisor, you run virtual switches. And these virtual switches create an overlay network using protocols like VXLAN, where basically, for example, this virtual machine, this is a virtual machine, you want to give them the impression they're connected to the same switch, then this virtual switch will take the packet, encapsulate it, stick the layer 2 into a VXLAN, send it over, tunnel it over, then it will get decapsulated and delivered. So basically, as long as the V switches know what to do, they can provide any layer 2 network abstraction on top of these hypervisors they do. Make sense so far? So in my count, network virtualization, if you just go by number of production deployments, network virtualization is by far the most widely deployed type of SDN today. Right? It's dominant in the enterprise and in the service provider data center. I've never seen it in the hyperscale. At least it's rare in the hyperscale, and that's primarily because these guys don't run hypervisors. Right? Because it uses hypervisor, also as of today, only works in the data center. Right? You couldn't use it for WAN, or at least in this form, you couldn't use it for WAN or a really nice property of network virtualization is that it's very easy to deploy because you don't need to make any changes to hardware. You just take your existing network underneath, use it for simple packet forwarding, and then you can put a layer on top. Right? So if you are running a large IT organization, that's actually a big deal, right? But they can just do things in software or they can do it in hardware. The hypervisor switches, there's actually very good open source ones available. Open vSwitch is pretty much the standard. There's another one, Indigo. They're open source, they're production quality. What's in open source at this point is the same what's running in production. So doing very good here. The control planes, building these control planes for these virtual networks, I think for any SDN, is pretty hard. It took us a big switch, I think 3 tries to get it right, and I think at Minnesota was about the same. Is that right? Mm-hmm. So the building a control plane that just works is not hard, but making it scalable and coping with error conditions is really, really complex. So most of the ones I've seen in production today are closed source. There's a few open source ones available, but they're typically more like a proof of concept or pilot type of ones. I haven't seen one in large scale production yet. There's 2 flavors of these. You can either say, I'm going to centralize all my control plane in one place. Right? And if you do that, I mean, you never only have one server for redundancy reasons, so you want and performance in most cases. So you want to split this up. You either go with the DHT or you have some kind of database replication model to spread the state out into multiple machines. There's also sort of a set of fully distributed ones. They're often BGP based. They still have a centralized unit for the API and the visiting user interface. But the idea is you just have a fully distributed state replication mechanism where every switch participates in the overall network. One thing, this is again, the slides in 2009 here, but back then our vision was to say, can we take the switches, take the sort of basic networking functionality, the operating system out of them, and take the applications and move them out, make the switches very simple, right? And in retrospect, I think this totally worked, right? In both of these approaches, typically most of the smarts are now sitting in a centralized controller. The switches have gotten a lot simpler. As you remember, the network virtualization, when you have basic layer 3 forwarding, you can set them up as a single sort of ECMP fabric. You never touch them again, right? Very, very simple. Now, what didn't quite work as effective was the open interface to hardware. Right? These are either it's in the network virtualization mode, you don't care, or it's a proprietary interface. And typically, the network operating system and the app are actually sort of not cleanly separated, certainly not with an API between them, right? So it turns out, I think the reason is that taking an application and basically sandboxing it in a way that's isolated from another application, while at the same time using a network efficiently, is a really, really hard problem, right? We've done with Flowvisor, I mean, we had a way to basically partition apps, but then you couldn't do a whole lot with your network. You couldn't basically it wasn't an easy way of sharing multiple services for one host. And basically, if you try to sandbox them tightly at the higher layer, we really haven't figured out how to do that yet. At least I haven't seen a solution there. So, the networks are typically what you would call the network operating system are pretty much fused together, so that they know how you forward packets, how this integrates with higher layers, it's pretty much still a vertically integrated thing with limited APIs. Now, typically all of these controllers up top have fairly rich APIs, like REST APIs, that you can use to program them. So they're quite programmable. We moved away from CLI, but this really open architecture, I think, never quite hasn't materialized yet. Maybe it will. So the second flavor that I would call SDN is bare metal switching. Right? And so here are 9 of, this is probably last year's, or even the year before, typical top-of-rack switches in a data center. Does anybody know what do they have in common?
Closed source.
Yeah, in fact, Trident Plus. Well, so they all have the same networking chip. Right? And the networking chip pretty much drives all of the performance characteristics and all of the sort of real-time forwarding functionality of the chip. So they're all the same L2 LP table sizes, they have the same number of ACLs, same throughput, largely identical speeds and feeds. Right? During this time, there's a transition from PHY to PHY-less, so that might impact your latency, but if you're in the same category, you have pretty much the same latency as well. If you measure these out, we did that at Big Switch, they're for all practical purposes indistinguishable. Right? So you can't from the data not tell which of these boxes you're running. So we've seen basically switching hardware in the data center as of today is commoditized. If you actually open them up, so I'm collecting photos of the motherboards of switches. And, so here we have two of these switches, and if you look at them, even the layout is fairly similar. Right? You have your network in the middle, you have your CPU module up here, right? PHYs, the actual connectors, power supplies. So this one has the power supplies on one side, but other than that, CPU, networking chip, PHYs, connectors. It's pretty much the same thing, right? I mean, how many of these work is that Broadcom will put out a reference design, right? And then the OEMs will come in and figure out, hey, let's shave off a couple of cents by taking programmable timer and replacing it with a fixed timer or something like that. So they tend to be very, very very similar in terms of how they're designed. There's a few exceptions, but most of them are. In fact, some of the low-end vendors at this point actually simply go to one of the large contract manufacturers and say, "Hey, I'd like to buy 10,000 of these, and please put this bezel in the front." Right? So they don't even design them themselves; they rely on a outsourced partner for that. So bare metal is just starting out in the enterprise data center, but it's today widely deployed, and actually it started in the hyperscale a long time ago. In some cases now they're actually building their own switches, as you might have seen from Google and Facebook, but others are still busy just ordering standard switches of their devices. Bare metal is just starting in the enterprise, so there's now a few banks have started deploying them, a few service providers, but it's still early days. On the switch side, there's actually a fairly good production quality stack available for very simple switch software, and I'll talk about that in a second. The main bottleneck is getting access to the SDKs. So if you want to program the chips on these switches, you typically have to get an agreement in place with Broadcom. That used to be impossibly hard. Now it's just hard. But as an individual, it's still difficult. And it's getting a little bit better. They're starting to put out open source versions of these SDKs, but they still don't have the functionality of the tools yet. In terms of control plane, there's different flavors. Right? Some actually just run this with a local control plane, so no centralized control plane. If you call this SDN or not, then my version may vary, but there's like Cumulus or PK8. They're basically just offering software that runs in these specific switches. Big Switch is a centralized control plane. There's also hybrid ones. Like if you look at what Google did in the LAN, there's some BGP going on. Then there's a centralized control that comes with bandwidth management. So some people mix and match the solution. The nice thing about bare metal switches is that at this point, there's a pretty comprehensive open source stack available. Right? It used to be actually really hard to program these things just because getting the software on a switch was hard. I mean, you have to pretty much open up the box and inside remove the CPU module, and then you can connect to reflash the flash. So at this point, pretty much all the bare metal switches out there are shipping with the only bootloader. So that's a basically a piece of code. It'll like PXE boot. It'll check on the network. Is the server that has an image for me? If yes, it'll store the image. Open networking Linux, which now is actually part of the OpenView project. It's basically a baseline Linux. So this doesn't help you when you're on the 40, because it just has your fan drivers and your memory maps and all the boring stuff to get the Linux operating system running on it. Then you have your networking chip API. And there's an open source one with limited functionality. They're expanding that. Actually, it's not fully open source, but it's open. You can obtain it without any problems. Then you have forwarding agents on top, and you can put a controller against that. So that's so my current take is I think bare metal switching is gonna. If you look 5 or 10 years from now, bare metal switching is going to be the standard in networking. I think we're basically converting towards a model where you buy hardware and software for these for networking hardware. So it's the same way how we've done it for PCs for a long time, right? The same thing is happening in storage. So people were basically a whole to a bare metal everything data center where standardized on small number of hardware components, and then you have software that runs on top that basically drives the functionality. So this sort of, just to give you a quick tour of how is SDN actually being deployed. Now, the next question is why actually enterprises, and generally, when I come to a network operator is deploying this, and there's a little bit focus on the enterprise because it's the same thing with this. But this is if I look at this, I think there's 3 primary drivers. I mean, the first one is automation, the second one is hardware independence, and the third one is storage. So, back to that early slide, right? The way how we run networks compared to the way how we run compute is very much Stone Age, right? We still use CLIs, it's still a very manual process. Here's a chart that shows how from 2007 to 2012, the efficiency of your average administrator for a server instance basically increased, right? So basically in 2007, one full-time employee could manage about 12 servers, and here we were up to a little under 50 by 2012. Right? So this is pretty amazing. Over a couple of years, we got a factor of 4 or so in efficiency. I've never found a similar graph for networking. That's what the anecdotal evidence suggests. It's pretty much flat. Right? The number of switches one network administrator can administer hasn't changed substantially over the past all this time frame. So the hope is that with software-defined networking, you can get the same increase in productivity for your network administrators. So the basic idea how it works is that you predefine templates, right? You say, here's a template that describes a couple of virtual machines. But in addition to that, it describes layer 2 networks, routers, firewalls, load balancers. And then basically, if you're an administrator, you can pick one of these templates that instantiate your entire system, right? So some people may know this, like for example, OpenStack has something called heat. Does anybody know heat here? So this way is something where I can define, here's my compute resources, my networking resources, storage resources, everything in one go, and then just instantiates all this. Amazon has some similar cloud formation. I think that's what Drive works. So this is the basic idea, right? Now, if you want to do this, the first thing you need to do is you need to have sort of a converged consumption layer on top of the infrastructure. Right? And this is something which your typical enterprise at the moment is trying to get to, but probably doesn't quite have yet. Right? So you basically, right now, the way you configure your servers, your network, your storage, and everything, you're doing everything separately. Right? You have basically different consoles, you also have different teams. Right? Your classical IT team has a networking team, a server team, a storage team, and basically trying to get to a point where all of these guys work together, but even more, ideally, where you have a joint interface to create all of these things in one go. There's OpenStack. Probably you've heard of, VRA is a product from VMware that does this. So that's sort of what everybody's trying to get to. If you can get it there, you can make orders of magnitude in gains in efficiency. So to give you an example, I once visited a customer, and they were about to migrate an application. So there's a couple of physical servers with VMs on them, from one rack to another rack. Right? So how hard could this be in a large enterprise data center? They had written a 79-page document on this application migration, right? And the majority of it was actually the network, because they had to change routes at the router, they had to create new VLANs on that side and attach them to the router. they had some firewall rules, so they had to buy a new firewall, put it over there, extract the rules from one firewall, stick it in the other firewall. They had to do the same thing with the load balancer. Then these applications had some bridge networks to another application, so they had to do these things. Then they had a meticulous plan how to do all of this very slowly, in phases with testing to make sure there's no service interruption. Because basically, if you put a wrong rule in the firewall, right, this can take out another of your production applications. So often what these enterprises do is they say we have a maintenance window, then you put a rule in the firewall in learning mode, you see how often it triggers, and if you convince yourself that it triggers correctly, then you actually in the next maintenance window you switch it up on really on your firewall as a rule that actually enforces something. So what I'm hearing from enterprise today is often takes 2 weeks to get a new layer 2 segment, new set of firewall rules done in the data center. Right? This is incredibly static. While your virtual machine is pretty much the same. Part of the problem here is that there's many little levels of interaction between the policy you're trying to express and how it's actually enforced. If you think about it, at a high level, what you'd like to say is something like, application A can't talk to application B. Okay, it's a good rule. Now in practice, how we express this is to say, well, application A has this type of virtual machine image for the web server and this type of virtual machine image for the database. And each virtual machine image has a couple of instances, and each instance has a couple of IP addresses. They often have multiple interfaces. So, and then you basically code the firewall rules as all of these different IP, these different IP addresses, which can talk to which. Right? And so at the end, if you look at the IP addresses and you're asking the question, from which application does this actually originate? It's often a very, very difficult question to answer. Right? I was in a bank once. They had 2 people that had the full-time job to look at a batch of 180,000 firewall rules and find out why they're there. They didn't know anymore, right? So this is really, really complicated. Now, how you automate, there's actually different flavors, right? You can either use this as a set of more powerful tools for your networking team. You can use this as basically to do things more real time, right? For example, to dynamically react if there's changes in your network, you want to reconfigure it. You can use it as self-service for employees. So there's now some organizations where basically you're a developer and you want to have a new network, you just go to self-service console and say provision, you get your new network. Your router, IP space. Or you can just use actually create a public facing service, an external facing service, public cloud. So the third major reason that I see why people are adopting this is this idea that basically by having a software-defined network, this isolates you from the physical network. Right? And that's a pretty powerful thing, because for example, imagine you have a data center, and for some reason you're changing the type of switch you're using. Right? Maybe it's just a generational thing, you go from the old to the new generation, or maybe you're changing vendors. Right? It used to be something that's really complicated, because up here you have the applications, and all the network configuration for the applications used to be down in the hardware. Right? So if you switch to a different vendor, some of these configuration options may no longer be available. Right? So you have to sort of carefully think through how do we adapt each and every network configuration to the new landscape that we have. Now, if you have a software-defined network in between, you basically can swap out the physical hardware. As long as the software-defined network can instantiate the same primitives on top of the new hardware, you don't care. Right? The same idea is with server virtualization. Right? In server virtualization, I don't like the server I have, I migrate away my virtual machines, I throw away the server, I put in a new one, I migrate the virtual machines back. Right? Now I can do the same thing with the network. I have a rack with switches, I want to refresh the rack, I migrate everything, including the network configuration, to a new rack, or replace my rack, and then I migrate it back. Whether the servers, the network is the same or different, that doesn't matter. It's a very powerful concept. It's in fact even more interesting if you're running with multiple data centers. So one of the main reasons why we at VMware will see people adopting network virtualization right now is that basically they're saying, for disaster recovery, keeping 2 physical data centers in perfect sync and how the physical network looks is really, really hard. But if you have network virtualization in between, then basically you can have slightly different hardware configuration. The virtualization layer will make sure that they both look the same, right? And now I can have my name, my backup data center, different hardware, it doesn't matter anymore. It's much easier to replicate all the software. That's a major use case. And then the third one is security. So 2014 overall was a pretty bad year for security. You might have seen Home Depot, Target, JPMC, largest bank, right? The second largest retailer. In Target's case, the CEO of Target was actually fired over the data breach. It's a great way to get the visibility down from the director of networking up to the CEO level. If the CEO gets fired, then suddenly everybody's very motivated. If you look at the attacks from last year, one thing has changed is that these attacks were very, very sophisticated. Right? So typically, what happened is that you had an attacker. The attacker would somehow find a way through the firewall, right? And they had different ways of doing this. They would, use a spear phishing attack against somebody who would actually physically steal hardware or break into an office just to get access to one server. Right? Physically steal access credentials, pay somebody off. Typically, this first server they're breaking into is actually not a particularly strategic one. Right? It's, some dev system or some contractor system. But once they're behind the firewall, they can basically now move around and start infecting other systems. Because the way a typical enterprise network is structured today is that you have a firewall on the perimeter, but inside you have very little controls. So I talked to a very large bank in New York 3 weeks ago, where they have all of their production applications running in one flat L3 network without any controls in between. So they have no visibility in which machines connect to which other machines. They have no visibility if somebody's snooping on the network. They have really no idea what's happening there. Right? So there's clearly a problem. Right? Now, what you'd like to do is you'd like to say, can we just put up firewalls everywhere? Right? Stick a firewall between every pair of virtual machines here. Now, it turns out in practice, there's two problems with it. I mean, the first one is just sheer bandwidth. If you want to take all of your east-west traffic in data centers, so basically all the traffic in data centers, and firewall it, that means your firewall needs to have the same capacity as your total rack switch, right? Make sense? So what's the capacity of a modern total rack switch? Roughly terabit or so. So it's not right. So if you have a terabit of capacity, a terabit of firewall capacity is $1 million or something like that. At least a good fraction of it, and it will take half a rack, right? I found one customer who actually does that. I'm not happy. So that's the first one. The even bigger problem is the administrative problem, right? We said before that managing firewall rules in enterprise today is really, really hard because it's many levels of indirection. If you take all your east-west traffic in firewall, it would have by an order of magnitude more firewall rules because most of the traffic today is inside, most of the connectivity is inside. So, doing this in practice, I found one organization, they have very special needs that sort of doing this in a small scale, but practically speaking, this is today impossible. And so here's actually a slide from VMware. Basically, how you can do with network virtualization is you can say, you can build a firewall into your hypervisor switch. Right? So basically, when you deploy a virtual machine, you deploy firewalls automatically to the hypervisor switch. And then if the virtual machine sends out a packet, it's because it gets a software firewall that intercepts the packet. It's a really nice solution because it scales out, right? You're not dependent on hardware boxes. And also the management of the rules is much easier because if you, for example, move around virtual machines, right, the firewall rules move with them, and if you just delete the virtual machine, then the firewall rules go away. So I can't speak for the industry as a whole, but if you look at VMware, I would say that right now probably 40% of adoption is driven by security. That's the primary reason why customers deploy SDN. About a little under 50 is automation, and a little over 10 is this idea of hardware independence and business continuity. Does that make sense, everybody? Any questions on use cases? No questions whatsoever. All right. Okay, so the last thing I want to talk about briefly is deployments. So deployments are tricky because right now there's very few companies that are publishing deployment numbers. And, that's the first problem. The second problem is all this software is still pretty new, right? I think the first production quality SDN deployments that sort of went beyond an early adopter community probably 2013 or so. I mean, we had the first software shipping and going to production probably around 2010, 2011, and but really becoming mainstream is only something that's happening right now. Right? So these are easy numbers for me because I just looked them up. So the last numbers we published at VMware was we have 400 customers at the end of 2014, about 70 production deployments. And to explain the gap here, right? It usually takes a fair amount of time. If you have a large bank, for example, and they buy a couple of $1 billion worth of SDN, between buying it and actually being in production, that can easily be be a year, right? We're growing roughly 4x year over year, right? So this is exponential growth, and we're doubling every 6 months. This means that even if 100% would go into production, you only would have 100 or so that are in production. This actually, this is a very good number. Now, I don't have good visibility into the rest of the industry. There's a couple of other companies. Probably add another 100, 200 customers with the overlay model. I don't know about production deployments. So bare metal switching in terms of deployments, and actually production deployments I'm aware of, I'm pretty sure there's over 100. I don't know exactly how many. And so there's a press release from a company that they alone have over 1 million ports now for the bare metal switching model, which I think is credible. So, but my best guess here is it's over 100 and over 1 million. So.
Who's that?
Humorous. It's very concentrated, so one hyperscale, but still, it's an impressive number. So we're seeing. I mean, these are pretty good numbers, pretty good production. Some of these production points are pretty large. VMware published another number that there's now over 50 customers that spend more than $1 million on SDN. Right? If you look at pricing over $1 million, that's pretty large point. It's no longer a POC, but that's so a good chunk of the data center. There's been published cases of tens of thousands and possibly about 100,000 of virtual machines, in a single deployment. So these are really large deployments. They're very nice to scale. In terms of who is deploying this, so again, the same problem is there's not that many customers that have gone public. I mean, at the end we have about 20 or so out of those 400. But to step through a few of them, so Rackspace, I know better than I do actually. That's one of the early customers of the server. They are actually Rackspace, NTT, and Join. They're all running essentially public clouds, or clouds for like customers at least, using software-defined networking. NTT as a Vodafone is interesting because they actually do network function virtualization. So this is not targeted at their customers, but this is basically to replace their own internal telco functions with SDN. We have about 80% of the large banks in New York at this point as customers for VMware. So we're seeing broad traction there, some very large deployments. We also announced the first transaction above $10 million for VMware. So these are really some very large deployments. TradeStation is actually a really cool company. So they're also public reference. They basically have a platform for stock trading and currency trading. Right? They build a server, and so they have customers, which are other banks and hedge funds that build trading applications on top of their platform. They use network virtualization to build a self-service for developers to create multi-tier apps, which is really cool. I mean, then you can so it's self-service, automatic provisions networks, firewalls. And you can do this in financial industry, and most of it in securities trading, which is massively regulated, right? So it's that you can drive something like a use case as complex as this at the end today. I think it's a lot of Columbia Sportswear is another nice one. There's a big case study, a public case study about them, where they're basically using this for their internal IT team to be a lot more agile and deploy these type of solutions. That I think I'm at my time budget here, isn't that correct? Mm-hmm. All right. Well, thank you. And questions?
Thank you very much.
Yes.
One question regarding the future that you see in the community and the industry. So you hinted at that we should maybe look at more the semantics and policies of networking. When are we going to move away from actually virtually building networks, like in OpenStack you plug in virtual switches and virtual routers, and build virtual firewalls? We don't want to look at that and recreate the mess that we had before.
Yeah, I completely agree. So
how will that work?
Yeah, I mean, if you take a big step back, right, and assume nothing had been invented so far, right, and then you just, if everything we know today, right, how would you how would you define firewall rules, right? And you would probably, my guess is, you would probably, as your primitive, have something like a segment, right? So most modern applications come in tiers, right? And so you have a web tier with a couple of web servers, you have an app tier with a couple of app servers, and you have a database tier, for example, right? And so the way how you would like to express firewall rules is to say the web tier can talk to the app tier only on this port, right? That's all. You turn this thing to sort of a microservice with a clearly defined interface. So there's now a couple of products where you can actually start doing this, right? So where you can basically define your firewall rules, your policy at that high level, and they get broken down internally and enforced internally, right? Which is actually really, really nice. I mean, you can do things like you change your IP subnetting, and your firewall rules don't change. Right? That may not seem like a big deal unless you've ever done it. You know, it's a huge effort in an enterprise if you change IP addressing. You can even go from a layer 2 to a layer 3 connectivity without changing firewall rules, which is kind of cute, right? In firewall broadcast packets and things like that. So I think that's what we're trying to go to, right? How are we going to get there? I think that the biggest bottleneck right now might actually be the consumption layer, right? Because I think, I'm not speaking for VMware here, but for the consumption layer, being open is kind of important because unless you buy your entire software suite from one vendor, right? You probably want this top layer that ties everything together to be vendor independent, right? At least at the end of that, right? So something like OpenStack would be great. I think unfortunately OpenStack is progressing a lot slower than people would like. I mean, it still doesn't have the stability, the functionality that you would like to have for the enterprise. So I think that's the bottleneck gating it. If that was moving more quickly and you had the functionality up there, changing your networking, software-defined networking products to actually take those high-level rules and breaking them down, right, and enforcing them at the lower layer by whatever method you need, right, would go a lot faster. I think the second thing is, it would be really nice to have sort of more standardized protocols where you can embed meta information, right? So, for example, if I'm sending a tunnel packet to you, right, we're both hypervisor switches, right? So you have VM running, I have VM running. I'm sending over a tunnel packet. Honestly, you don't really care that much about the IP address, just to make sure it's the right one so the other virtual machine will accept it, right? And the things in the protocol header, we'd really like to have something in there like an application ID or a segment ID, or the ID of the virtual machine, because those are really the things we like to enforce primitives on. And so having, there's like Genève and these efforts. So having more advanced protocols there, that allow you to embed more of the meta information is really powerful. Yes.
So when you said that the original OpenFlow model got a little traction, is that because of technology or is business or a little bit of both? And is the Cumulus networks model much different from that then?
I think it's not because of technology, right? I mean, the OpenFlow protocol is used widely in industry under the hood as a communication protocol, right? It's in many places. The problem is it's not a lack of OpenFlow. The problem is the lack of standardized OpenFlow, right? This idea of you buy a switch from vendor A and control from vendor B, right? That hasn't really materialized because building solutions right now still requires you to control both ends because things are growing so rapidly. So I think it's not a technical argument. It's more often business or organizational maybe. It's not even business, organizational argument. Does that make sense?
Yeah. So you said that the Cumulus networks model is similar, but they're being more successful.
Cumulus just builds the software that runs on the switch.
Right.
So
it's not OpenFlow, but still software on bare metal switch. It's similar, is it not? Or
but OpenFlow is a protocol between a control plane and a switch. Right. Cumulus doesn't have a centralized controller.
Yeah, it doesn't.
So they don't have that problem. They have a different architectural model.
Mm-hmm.
Does that make sense?
I guess so.
So OpenFlow, you have a controller, right? And then you have switches.
Yeah, but I thought your argument was about it's a business model, right? You buy the software from vendor A, you buy the hardware from vendor B, and you said that didn't work.
No.
So that works.
Everybody loves the model of buying software from vendor A and software from vendor B, right?
Right.
As long as it perfectly works together. So I think that the hard part of the original OpenFlow model was you bought the hardware plus a little bit of software from vendor A,
right?
And then the controller software from vendor B, and they didn't work together. I mean, they didn't at least weren't able to innovate as quickly as you would like. Does it make sense?
Okay.
Yes.
So most of your examples were enterprises, understandably.
That's
right. So what do you think happens in the service provider, the WAN, with everything that AT&T and Verizon have been saying?
Yeah.
What happens there?
Look,
and you think the technology evolution will be different, right? Or very similar, will follow similar?
it's a great question. I think my impression is that the WAN SDN space is maybe where the enterprise was 3 years ago, right? Where it was last year was mostly talking. Now we're actually seeing them experiment. Not so much production, but experiment.
Sure.
And usually that's followed by production at some point. So the first question is, what are the use cases for like the WAN, for SDN WAN, right? And it seems like the number one is this idea of running very simple tag switch networks, where the set of challenges there, I think, is very different from what's in the data center. You have a smaller set of endpoints. You have I would argue, fundamentally simpler problem, right? Because it's more, you're a lot more prescriptive. But you also have much even more stringent uptime guarantees in more partitions, right? So that makes it harder again, right? Structurally, it's something for which standardizing that seems a lot more manageable, I think, than what you do in the data center, right? I mean, I think the hard part will be getting the details around failover scenarios right. I mean, that has proven hard for standardizing these protocols in the data center. Now, like, what do you do in case of controller being disconnected and you have to do, become an up responder or something like that? But that's something which was anticipated. The open source protocol, there's no clear standard, and as long as that doesn't exist, you could use an off-the-rack switch. So I think I'm hopeful. Let me put it this way: I'm hopeful that then we can go more for standards.
And do you think that eventually the control plane becomes predominantly open source because it's kind of an essential but non-differentiated piece?
Overall, look, long term probably, right? But it could be quite a while. Maybe my simplified model of how I think of open source is to basically say, whenever you have a software industry, no matter what, right? You start with innovation. At some point, part of this becomes commoditized, right? It becomes simpler and simpler. Then the commoditized part, becomes open source. Because somebody figures out I can't make money anymore. Let's just push, and I don't want anybody else to own this, so let's do an open source implementation for the market. Right? That's usually how it happens. And so, for right now, for a very simple L2, L3 overlay, right? I think we're at that point. Right? That's my personal opinion. And we're starting to see open source solutions that are there. Now, when it comes to scaling them, putting on the management layer, and giving sufficient visibility, that's not ready yet, right? So the question is, are these two, is this separable, right? If at this point it would be cleanly separable, my guess is we'd start to see a bifurcation, like we'd start to see open source splitting off, and then after some time everybody converging on the open source. But these things are currently too intrinsically linked, right? I mean, I don't know, I wouldn't know how to break out something at a complete network scale that you could build on top. Does that make sense?
Yeah, somewhat. Yeah.
So I mean, at this point, I wouldn't expect this to go open source in the next 3 to 5 years. They can control it.
My own opinion as to why it's been difficult to have a meaningful, standardized, open interface like is the sort of mismatch between the flexibility of the software above, and then, as you mentioned, this opaque and closed fixed function hardware below, which you've got this constraint that you're trying to map down into, which is opaque most of the time.
No, look, if you had different hardware, and I wholeheartedly agree, then it's time to rethink that.
And clearly, if you have if the switch underneath is software, like OBS, then that can evolve much faster.
Right. Absolutely.
So instead of thinking of it as a top-to-bottom software, it's a programmable approach as an OPM.
But even then, you need, I think it'll take care of part of the problem, which is the forwarding part. Practically speaking, the complexity in running an SDN control plane with switches is half forwarding, well, 3/4 forwarding, but there's 1/4 of other, right? So coping with failover scenarios, the sort of failure detection, certain type of local repeaters you need on these switches for edge cases, right? So I think we need to figure out a way how to get a software footprint on the switch, whether physical or virtual, right? That can be, how about the following? If you have a graphics card, it comes with a Windows driver, right, to fully leverage the graphics card. You might need the same thing where you say, I have a controller from company X, and you need a driver, for a particular piece of hardware, right? And yes, you can access a graphic card in a 640 VGA mode without a driver, right? But really, to squeeze out the last bit of performance, you need the latest NVIDIA drivers, they're updated in real time. So I think, you can do either, but I don't think this will go away anytime soon.
Okay. Let's thank Guido again. Thank you.
Thank you.